All right, today we're going under the hood of the Java machine. We're going to peel back the layers on one of the most popular programming languages on the planet to see what makes it tick. It's an incredible piece of engineering, so let's get right into it. Everything starts here, right? With a single line of code. Pretty much every programmer on Earth has typed this exact line. It seems so simple, but the journey it takes from your editor to your screen, well, that's where the real magic is.
So, that's the big question for this explainer. How does Java take this simple, human-readable command and turn it into a running application? It's a fascinating story of translation, optimization, and some seriously clever thinking.
Our very first stop is compilation. You can think of this as translating our code, which is kind of like English, into a universal language that any Java machine anywhere on Earth can understand. This is the absolute bedrock of Java's famous write once, run anywhere promise.
And that universal language is called Java bytecode. Now, what's so special about it? Well, it's not written for a specific computer chip like an Intel or an ARM processor. No, it's written for a virtual machine, the JVM. And that one idea right there is the secret sauce to Java's legendary portability.
And here you can see that translation in action. On the left, we've got the simple Java code that we write as humans. And on the right, that's a sneak peek at the bytecode it becomes. You see these little instructions like iload to load a number or iadd to add them together. This is the actual blueprint the JVM works with.
So you have these blueprints. How do they actually get into the factory? Well, that's the job of a component called the ClassLoader. When you run your application, the ClassLoader is the one that goes out, finds these bytecode files, and pulls them into the JVM's memory. But only right when they're needed. It's basically the gatekeeper for our entire virtual factory.
Okay, so loading the blueprints is one thing, but running them crazy fast is a whole different ballgame. And this brings us to the real heart of Java's performance, a brilliantly smart assembly line known as the just-in-time or JIT compiler.
So here's the problem the JIT was built to solve. If the JVM just read the bytecode one instruction at a time like a simple interpreter, it would be painfully slow. So how in the world does Java manage to compete and often win against languages like C++ when it comes to raw speed?
The answer is just-in-time compilation. See, as your application is running, the JVM is constantly watching. It's profiling your code, looking for the parts that get executed over and over again. These are called hotspots. And when it finds one, the JIT compiler swoops in, translates that bytecode directly into super optimized native machine code, and caches it for next time. It's brilliant.
This whole process, called tiered compilation, is even cleverer. It doesn't just happen once. At first, a quick and dirty compiler called C1 gives you a fast speed boost so your app starts up quickly. But if that code gets even hotter, a much more powerful C2 compiler takes its time and applies some really aggressive optimizations for maximum long-term performance. You really get the best of both worlds, a quick start and incredible speed over time.
And the tricks the JIT uses are just amazing. It can do things like inlining, where it just gets rid of a method call altogether, or it can unroll loops to make them faster. It can even find and delete dead code that it proves will never ever be used. This is why Java applications often get faster the longer you run them. The JIT is always learning and optimizing.
Now, high-performance factory has to be kept clean, right? Otherwise, things grind to a halt. In the Java world, that means managing memory. And this is another area where the JVM is a total rock star, thanks to its automatic garbage collector.
The best way to picture Java's memory is to think of it like a giant warehouse. All the things, or objects, your program creates are stored in this space, which we call the heap. And the JVM has a really clever system for keeping this warehouse organized based on how old the objects are.
This system is called generational garbage collection, and it's based on one simple, kind of morbid observation. Most objects die young. So new objects are born in the young generation area, which gets cleaned up super frequently. But if an object manages to survive a few of those cleanups, it gets promoted to the old generation, which is cleaned out way less often.
This makes the whole cleanup process incredibly efficient.
But what happens when that system breaks down? You get a memory leak. This is when your application accidentally holds onto an object it's never going to use again. The garbage collector sees that your code is still pointing to it, so it thinks it's important and leaves it alone. It's like you're holding onto an empty coffee cup forever. Eventually, you just run out of hands to hold anything else.
Now, this JVM factory isn't some museum piece. It is constantly getting upgraded, so let's take a look at how modern Java has evolved, because it's led to some absolutely revolutionary new capabilities.
You can see this clear path of innovation just by looking at the major releases. Java 8 gave us lambdas and a new way to think about code. Java 11 modularized the entire platform. Java 17 gave us more powerful ways to model our data. And then came Java 21, and it brought a revolution with it.
And that revolution was something truly game-changing, especially for building the kinds of massive applications we need today. It's a whole new way to handle countless things happening all at once without bringing your entire system to its knees.
See, for years, doing many things at once meant using what are called platform threads. But each one of these is a heavy operating system level thread that eats up a lot of memory. On a typical machine, you might top out around 10,000 of these before the system just gives up.
Then, Java 21 introduces virtual threads. And on that very same hardware, you can now handle over 1 million concurrent tasks. That's because these aren't OS threads. They're incredibly lightweight tasks, managed entirely by the JVM. The jump in scale is just mind-boggling.
So what does this actually mean for developers? It means we get massive scalability, especially for apps that spend a lot of time waiting for networks or databases. It means we can go back to writing simple, easy-to-read code. And we get all this with way less memory and CPU usage. It's a huge win.
For decades, we treated threads like a precious, expensive resource that we had to manage carefully. And now, they're basically free. This leaves us with a really exciting question. What new kinds of software, what new architectures become possible now that one of the fundamental limits of computing has just been erased? I think the entire industry is about to find out.